All right, let's work through this. So we want to use integrating factors to solve this. And then what we want to do is we want to use Laplace transforms as another way to solve the initial value problem as well. And see that we hopefully get the same answer either way. To see that Laplace transforms works. Laplace transforms, as I hinted at on Monday, is for a problem like this more difficult. But what you're going to see ultimately in section 6.2 is that Laplace transforms apply to situations that, for example, integrating factors is not so helpful for. In particular, if the right-hand side function, the forcing function, if you want to call it a forcing function, is even discontinuous, which is like modeling a hammer hitting a mass on a spring or something. That would be more relevant for a second order equation, a harmonic oscillator. But the idea is going to come across in section 6.2. So let's just quickly do the integrating factor method. So you want to let mu equal the e to the integral of whatever's in front of the y there, which is a constant in this case. Integrating factor method does apply to this situation, even if that's not a constant. I don't know if you remember that. Even if this 5 were, say, like a 5t or a 5t squared or a 5 over t, although if it were 5 over t, we would not think about the initial value at being at t equals 0. 5 over t plus 1 would be another option. The integrating factor method still works, whereas the undetermined coefficient method might be harder. Guessing yp in that kind of situation would be harder. So integrating factors is better, generally speaking, for this kind of problem than undetermined coefficients. Anyway, we can use e to the 5t as the integrating factor. You don't need to add a c. Adding a plus c is okay, but you don't need to. You multiply both sides of the differential equation by the integrating factor, making it a factor of both sides of the equation. And the reason this is a good thing to do, don't forget to multiply it on the right side as well, is because almost as if by magic, it's not really magic, it's based on the derivation of the integrating factor, the left-hand side becomes the derivative of a product, and that product is always the product of the integrating factor times the unknown function that I want to solve for. Calling it y here, but y is a function of t, remember that. I could write y of t in there. And that means it's easy to integrate. That's why it's an integrating factor. Now integrate both sides. With respect to t, the left side is easy to integrate. You're integrating a derivative, therefore you just get the function itself, e to the 5t times y. We do need to do that integral, -1/2 e to the -2t, and we do need a plus c. Solve for y now by dividing both sides by e to the 5t. Equivalently multiply both sides by e to the -5t. Gives you -1/2 e to the -7t plus c e to the -5t. And do notice if we had used the method of undetermined coefficients, this would have been the yh and this would have been the yp. So it would give you the same thing in the end. Now use the initial condition. 3 equals y of 0, plug in t equals 0 there, get -1/2 plus c. So c is 3.5, which is 7/2. And the final answer, if I combine these things, is going to be y equals -1/2 e to the -7t plus 7/2 e to the -5t. Look okay? No mistakes? Get that? All right. Now let's use this method of Laplace transforms, which even if you're up with the videos where you should be, you haven't yet watched the video lecture about the Laplace transform, the first one, which is 34a. Even in 34a, I don't quite get to enough topics to help you as much as ideal for section 6.1 problems due tomorrow. So that's why I want to go through this example in detail. This will also help you for that more fully due tomorrow. What you want to do is you want to take the Laplace transform of both sides of that differential equation. Apply this Laplace transform operator transformation. It is a linear transformation on function spaces, just like the derivative operator is a linear transformation on function spaces. I take L, and I like writing my L here as a cursive, L. Of both sides, so I plug the left-hand side of the differential equation into L and the right-hand side. So I can write the first step like that. What's the logic of what you're really doing? When you write a differential equation, remember, as it stands, the differential equation is neither true nor false. It's what's called an open sentence. And it only becomes true or false when you plug a function in, the solution in, or a solution in. But when you solve a differential equation, it's, in essence, the logic is you're assuming there's a solution and you're wondering what it is or what it must be. So I'm sort of really, in my mind, without saying so, assuming there's a function whose derivative plus 5 times itself simplifies to e to the negative 7t for all t, and also satisfies this condition. And then I'm assuming then if I plug that function into this operator, this L operator on this side and on this side, I've got to get the same thing because I'm assuming y satisfies that. I'm implicitly making those kinds of assumptions without typically stating them. I just stated it now. Big picture is you're trying to now use properties of Laplace transforms, for example, linearity. It's operation preserving. Laplace transform of a sum is the sum of the Laplace transform of the pieces. And some other properties we'll need to algebraically solve for the Laplace transform of the unknown function y. L of y will be some function of the variable commonly used as s. Why? That's just traditional. In general, L of y of t, here I'll explicitly put the t in there. Remember, by definition, is the integral from 0 to infinity of y of t times e to the negative st dt. It's an improper integral, assuming it converges for a fixed value of s. You could do the integral. Maybe it converges for many values of s. You pretend s is fixed when you do the integral, but then in the end, you get something that depends on s, which you can then change your perspective on and say, hey, that's a function of s. But the letter s is arbitrary. Other letters could have been used, r, u, v, whatever. It's just traditional to use s. Use the linearity property. The Laplace transform there is equal to the Laplace transform of the derivative plus the Laplace transform of 5y. The 5 can be factored out in front as well. Remember what I said a couple minutes ago. The goal is to solve for the Laplace transform of y. This seems to be a problem. That's the Laplace transform of the derivative of y, not y itself. So it's unclear how we're going to fix that problem, but it can be fixed. It turns out we can express the Laplace transform of the derivative of y in terms of the Laplace transform y. Let's do that first. Let's derive how to do that. By definition, this is the integral from 0 to infinity of dy dt times e to the negative st, which I'll write as y prime of t times e to the negative st. And whenever you see an integral involving a product, where one of the terms in the product, one of the factors of the product is a derivative of something, that should set off flashing light bulbs in your head saying, hey, probably integration by parts is helpful. I'm serious. Anytime you see an integral of a product where one of the factors involves a derivative, especially if it's an abstract derivative for a function you don't know, probably integration by parts is helpful. Let u equal something and dv equal something, or again, with our calc book, it uses v prime here instead of dv. You want u to be something easy to differentiate, and you want dv or v prime to be something easy to integrate. And you want them to multiply together to give you this entire thing, y prime of t e to the negative st dt, and the dt does have to go with the dv. Well, e to the negative st is both easy to differentiate and integrate. However, y prime of t, if I differentiate it, it's going to be y double prime of t, and that sounds like it's going to make things worse. So that's a hint that you probably want to let dv be y prime of t dt, or if you prefer, v prime equals y prime, and let u be the other factor, e to the negative st. Now find du with respect to t, negative s e to the negative st dt, or if you prefer, u prime is negative s e to the negative st. And v is going to be an integral, an antiderivative of y prime. Hey, that's just y. So the integration by parts formula now says, do u times v, which will be y of t times e to the negative st, that's getting evaluated from 0 to infinity, minus the integral of v times du, product of these two things. Notice there's a minus sign there on the left side. It's going to cancel with this minus sign to give you a plus sign. And the s can be factored out of the integral because the integral is with respect to t. What we're hoping, looking at this, is we're hoping it simplifies nicely. For one thing, we might be hoping this goes to 0. Technically speaking, when you put an infinity up there, it's a limit. I'm being a little hand wavy here. I'm being more like a scientist or engineer here in saying, yeah, that goes to 0 under some assumptions. What kind of assumptions? Typically that s is big enough, perhaps positively, to make this exponential decay go to 0 faster than y of t might go to infinity. And that'll certainly happen if y of t happens to be t or t squared or t cubed. It would also be true even if y of t were exponential growth, as long as, say, it was e to the 5t, as long as s is bigger than 5, it would still work, making negative s less than negative 5. This is really assuming s is large enough. Would it ever not be true, even if s is really large? It could be not true if y of t grew really fast, like faster than the exponential growth, which is possible, by the way. Like t to the t power is faster than exponential growth. Ever think about that? Or x to the x power? That's faster than exponential growth. We don't typically encounter functions like that in applications, but theoretically, y of t could grow fast enough that this doesn't go to 0, even if s is really large. But we're assuming. So that goes to 0. What about this? Well, that thing right there is the Laplace transform of y. Oh, I made a mistake. This doesn't go to 0. It goes to 0 minus y of 0 e to the 0. When you quote unquote plug in infinity, it goes to 0. But when you plug in 0, it's not 0. It's negative y of 0, actually. Sorry, that was a bad mistake. And this thing is L of y. So this entire thing now simplifies to S times L of y minus y of 0. And that is the answer. That is how the derivative, the Laplace transform of the derivative of y is related to the Laplace transform of y. L of dy dt equals S times L of y minus y of 0 under assumptions that y of t doesn't grow too fast. And S is large enough. Are those assumptions valid here? This is really ultimately our y of t, though we wouldn't know that ahead of time. And yeah, if S is bigger than 7, that's gonna, y of t times e to the negative st will go to, well, actually, this is exponential decay yet. So actually, S only needs to be bigger than -5. Because that's still exponential decay. We don't typically worry about it. It typically works out, okay? The key thing is this equals this.
How are you able to simplify that second part of the equation to the Laplace transform of y?
Well, for one thing, if I replace this with this, I've got two expressions involving the Laplace transform.
Right before it, right there.
Right here?
Right down, where it says like that S times integral is equal to S times the Laplace y, right there.
Because that's the Laplace transform of y by definition right there. It's the same thing that I wrote up here. Thanks for pointing that out. I should have emphasized that. These two things match. And they got the extra factor of S there. All right, still not done. We're far from done. Also got to figure out this thing. What's the Laplace transform of e to the negative 7t? Let's do a more general problem. What's the Laplace transform of e to the at, where a is a constant? By definition, that's the improper integral from 0 to infinity of e to the at times e to the negative st dt. This is typically written as the integral from 0 to infinity of e to the negative in parentheses s minus a times t. Right? Add those exponents and then do a little creative algebra, and you can write it that way. And that'll be exponential decay for the integrand as long as s is bigger than a. This converges if s is bigger than a. So that's the condition on s for convergence. And what does it converge to? Again, I'm being sloppy here by not putting limit signs. I think in the lectures I put limit signs. You should realize that technically speaking, you need limit signs to derive these things to be a more precise proof. I don't typically put these proofs on exams, though. Mostly on exams, you're just doing calculations, so you're using these properties. Turns out, here's your general antiderivative. And t is going from 0 to infinity here. And when you quote unquote plug in infinity, you get 0. And when you plug in t equals 0, you get that. That's 1. Two negative signs cancel to give you 1 over s minus a if s is greater than a. All right, now we got to go back to the differential equation. So again, we were at this step. I'll rewrite it. The Laplace transform of dy dt plus 5 times the Laplace transform of y equals the Laplace transform of e to the negative 7t. And based on what we've just done the past 15 minutes or something, this becomes S times the Laplace transform of y minus y of 0 plus 5 times the Laplace transform of y equals, what's the Laplace transform of e to the negative 7t? It's this when a is negative 7. 1 over s plus 7 is what that would be when a is negative 7. And look at this, almost as if by a miracle, the initial conditions in this equation. I can plug in the initial condition right now. Y of 0 is 3, right? Back to the IVP, y of 0 is 3. This is a minus 3. And remember, I said 15, 20 minutes ago, the goal is to solve this algebraically for L of y. I can write s plus 5 in parentheses times L of y equals 1 over s plus 7 and then a plus 3 after adding 3 to both sides. So I did 2 algebra steps there. And therefore, L of y, divide both sides by s plus 5, is 1 over, in parentheses, s plus 7 times s plus 5, plus 3 over s plus 5. That is the Laplace transform of the solution y, the unknown solution that I'm trying to find, which we did find with integrating factors, but that's what we're after. The last step here, though it's a long step by hand, is to find y from this. How? By essentially applying what's called the inverse Laplace transform to both sides of this equation. Because if you apply the inverse Laplace transform to that side, you just get y. The L inverse and L cancel. I could write y equals L inverse of L of y equals the inverse Laplace transform of all this stuff there. L is a linear transformation. Turns out to be 1-to-1 and onto as well. L inverse exists. Does L inverse have a formula? No, it doesn't actually. It's kind of analogous to the relationship between derivatives and antiderivatives. Every antiderivative fact comes from derivative fact. For example, the integral of 1 over 1 plus x squared is inverse tangent of x plus c. What's the reason? Because the derivative of inverse tangent plus c is 1 over 1 plus x squared. That's the reason. The integral is the inverse operation of the derivative one. This is x here. If you know this derivative fact, then you know the integral fact. Similarly, if you know a fact about Laplace transforms, like this fact here, that these two things are equal, then you know a fact about L inverse. L inverse of this thing is e to the at. L inverse of 1 over s minus a is e to the at. Hey, that's relevant for this one. A is -5. Compare these two. And there's also, well, there's a 3 up top. The 3 just gets carried along for the ride. It's linear, it's operation preserving. We can write this as L inverse of 1 over, in parentheses, s plus 7 times s plus 5 plus 3 L inverse of 1 over s plus 5, which I can write as 1 over s minus -5. And this then would be 3 times 1 over s minus, or excuse me, 3e to the -5t is what this would equal. Because of those being equal. A is -5. The 3 just gets carried along to the right. So the only thing left to do that's hard, it seems, is what's that? Did I make a mistake here? Oh, no, okay, not necessarily a mistake. I'm trying to think about how this compares to the actual answer. I'm trying to think about how it compares to this. I do see a negative e to the negative 5t in there, as there's a negative 5t there. This is not a 3. It's 3 plus a half. Somehow another half e to the negative 5t is going to have to come into play probably from this term. But how do you do that? Your old friend, partial fractions, just like with integrals, because doing an inverse Laplace transform, in a sense, is, yeah, kind of analogous to doing an integral here. Kind of. I need to figure out how to write 1 over s plus 7 times s plus 5 as some constant a over s plus 7 plus another constant b over s plus 5. And I hope that makes sense as a good thing to do, because then I'd be able to apply the inverse Laplace transform to both of those things and add the results. Solve for a and b. Multiply both sides by the common denominator to get a 1 on the left side. You get partial cancellation with this term. The s plus 7s cancel to give you this. And with the second term, when I multiply both that by s plus 5 times s plus 7, the s plus 5s cancel to leave you with an s plus 7. And your teacher now at this point with partial fractions may have said, go ahead and expand this out and set up a linear system of equations in the unknowns a and b, which is fine. However, it's a lot quicker just to plug in special values of s. I want this to be true for any s. So for example, it should be true when s is negative 5. And that gives me b is 1/2. There's the extra 1/2. And if I plug in s equals negative 7, I get 1 equals a times negative 2 plus b times 0. So a is negative 1/2. Oh boy. There, 3 plus a half, 7 halves, and there's a negative 1/2. We're almost done. A is negative 1/2. B is positive 1/2. B is over s plus 5. I already know this 3 to the negative 5t is there. This thing is e to the negative 7t. This thing is e to the negative 5t. The final answer is negative 1/2 e to the negative 7t plus 7 halves e to the negative 5t, just like we got with integrating factors. Yeah, it's harder. Is it more fun? Maybe. Is there a good reason to do it? Yeah, section 6.2 and beyond is a good reason to do it. Not justified really in section 6.1. They're just trying to get your feet wet. 6.2, when we start having discontinuous forcing functions, is when it gets more useful, because then integrating factors is just not so helpful. Theoretically, it could still be applied, but I don't know, the Laplace transform works out better. I'm not fully, it's not something that I study in depth, but I do also know that at the end of chapter 6, which we will not get to, stuff about convolutions and qualitative theory of Laplace transforms, it's the last couple sections of chapter 6. We don't get there. We don't have enough time. However, it'll come up in math methods. And it's really useful for electrical engineering, especially that stuff at the end of chapter 6. I know Karen Rogers really likes Laplace transforms. So if you're an electrical engineering major, over Christmas, you should probably read the rest of chapter 6. Well, okay, at some point, read the rest of chapter 6. I guess doing it over Christmas might not be such a good idea because you just forget it after you read it. So maybe when you're about to learn about be in the class math methods or some electrical engineering class where you're going to need this kind of stuff. What class? I don't know for sure. Maybe signals and circuits, maybe. I don't know for sure. But I do know you can ask her. She gets excited about Laplace transforms. And it is kind of a wetting your feet thing also with regard to Fourier transforms. Fourier transforms are related to Laplace transforms. They're a bit more general. Another thing you need with Fourier transforms is complex numbers. And you're doing integrals of complex functions. You can relate Fourier transforms and Laplace transforms. And that stuff's plenty of uses as well. It is also can be thought of as related to Fourier series. And in my lectures here near the end of the class, I talk about Fourier series. In fact, we'll do a little bit of talking about Fourier series here in a few minutes. As a way to both apply linear algebra, inner products in particular, and see that it's relevant for partial differential equations. Let's do two things relatively quickly. One thing is I want to emphasize for a few minutes the idea of a trapping region, and it's called the Poincare-Bendixson Theorem. And the main things you should look for in the lectures with regard to those things. And then talk a little bit about inner products and Fourier polynomials as a precursor to Fourier series, okay? My goal here, because we're short on time, is not to do in-depth stuff, just to give you a little feel for what to expect, okay? With regard to trapping regions, when I say a region is a trapping region for, say in general, a nonlinear system of differential equations written in vector form like that, where y in general could be a vector in Rn. More precisely, y of t is a vector in Rn for all t. Although a subtlety that I'm shoving under the rug there is that y of t, a solution of the differential equation, which I could also write like as a capital phi of t, might not be defined for all t. Typically with nonlinear equations, one theme I have gotten across sometimes is that the solutions are not necessarily defined for all t. They are for linear systems, but not for nonlinear systems. The basic idea of a trapping region, whether it's in 2 dimensions or 3 dimensions or some higher dimensional space you can't imagine, only by analogy, is that it's some region which would be maybe a blob in the plane or some sort of higher dimensional blob in 3 dimensions, or again, by analogy, some higher dimensional blob in 4 or 5 or 6 or 7 dimensions. And what typically happens for a trapping region is that the vector field defined by the right-hand side function, if you could somehow graph it, points inward along the boundary, typically. Imagine that these arrows are all pointing inward along the boundary. The base of the arrows is supposed to be on this surface that I'm drawing. And you need to imagine them going all into the region here. That is a trapping region. Because solutions that go into it are stuck. They have to stay in it as t goes to infinity. Because the vector field's pointing in, not out. There's no spot on the boundary where the vector field's pointing outward. So solutions that maybe have an initial condition outside the region, when they go into the region, they can't get out. What do they do once they're inside? Well, there's lots of things that can happen. The simplest thing that would happen is there's one equilibrium point that they all head toward, some sort of sink. That would be the simplest thing that could happen. But in higher dimensions, really, really wild things can happen inside the trapping region. But there's got to be solutions that stay inside the trapping region for all time, whether it's an equilibrium point or more than one equilibrium point, or maybe periodic solutions. There's got to be solutions that stay inside there for all time. That's one general fact to know about trapping regions. In the case of a trapping region in the plane, 2 dimensions, if n is 2, if you can somehow show there's no equilibrium points inside that region, you can say for sure there's a periodic solution in it. That's the Poincare-Bendixson Theorem. It only applies in 2 dimensions. In R2, the plane, our favorite space. And if you were going to have a trapping region that had no equilibrium points inside of it, it actually would have to be a trapping region that's shaped something like this. It would have to have an inner boundary and an outer boundary. If it only had an outer boundary, it turns out it would have to have equilibrium points inside, at least one. But if it's ring shaped like this, it could be a trapping region with no equilibrium points inside. And your vector field might look like this along the boundary. And the Poincare-Bendixson theorem, which can be proved, would show there's at least one periodic solution inside here. That's something you should know for the test as well. Final exam. In the lectures, I illustrate this with some actual examples of differential equations. And you'll see I verify that it's a trapping region using something called an outward pointing normal vector. And I use dot products as well, and polar coordinates, in fact, to come up with the differential equations to begin with. So you should look for those things. But once you've defined your trapping region, in general, trapping regions are difficult to find. Only for very special systems are they easy to describe. The polar coordinates that I talk about in the lecture are done so that I can come up with a relatively simple system of differential equations where I can do this kind of thing. To just illustrate the idea. But you should be able to do the calculations that I do. I didn't put them in last year's final, but I'm not ruling it out for this year's. I will share with you other kinds of differential equations examples I've done in the past as well. Should do that after class today. So that's stuff to look for in the lectures. That is stuff you should know the basic idea of and be able to do some calculations with. Other thing I want to mention, and then I'll just let you go. I'll let you leave if you want, or I'll stick around for people who might want to still ask questions. Other stuff I just want to emphasize here is the inner products, the projections in inner product spaces, and how it's related to Fourier polynomials. Just again, big idea here, what to look for. And ask me a question if you want me to clarify something. With Fourier polynomials and ultimately Fourier series, you can think of it all in terms of linear algebra. You could, for example, let W be the span of a collection of functions. And with Fourier polynomials, the goal in Fourier series, the goal is to both approximate and even maybe represent exactly arbitrary periodic functions as linear combinations of sines and cosines of different frequencies. That was Fourier's key insight, was that that's a good idea. And as an example, leading toward that, I could, for example, let W be the span of the following. Let's go with 5 functions. 1 cos t, sine t, cos 2t, and sine 2t. And I could start with an arbitrary function. F of t equals, for example, t cubed. I think in the lecture I do t and t squared. And I could say, what function in W that's a linear combination of these functions is closest to this function over some interval? Whoops. Somebody's trying to call me. It's spam here. That was unfortunate. Usually I put my phone on airplane mode. I just forgot to. Say that again. I'm wondering what function in W in this is a 5-dimensional vector space because it's got 5 functions that do turn out to be linearly independent, though that would take proof. This would be a basis. In fact, an orthogonal basis for W. All that would take proof. Or, well, it's only orthogonal if you pick the interval right. And for trig functions like this, you want to pick intervals that are, for example, 2 pi units long, like say negative pi to positive pi. I could have picked a different interval, though if you pick a different interval, you get a different answer. What function in W, what linear combination of these functions is somehow closest to f of t? That's the thing you're trying to answer. You're trying to approximate f of t equals t cubed with some linear combination of these, at least over the interval from negative pi to pi. Closest is with respect to some metric. A metric is a measure of distance in some abstract space. This is kind of an abstract space, though you can still describe it with linear algebra terminology and ideas. The metric on this space is going to be defined by the distance between 2 arbitrary functions f and g. Well, I should probably use different letters. G and h is also represented as the norm of g minus h. But what's the norm of g minus h? It's the square root of the inner product of g minus h with itself. What in the world am I doing here? I'm defining what distance between functions means in an inner product space, where the inner product in this case is defined by an integral. Oh, I need different letters even here. The inner product of, say, what should I call them? How about phi and psi is defined to be the integral over the interval from negative pi to pi of the product of phi and psi. This defines an inner product. Inner product is a generalization of dot product. What are dot products? What are we used to? You're used to dot products of vectors in Rn where you've got, say, two column vectors, and you add up the product of the components, right? This is analogous to that in a continuous setting. Integrals like adding, and there's a product of components. Well, sort of. Function values are kind of analogous to components of vectors, kind of, except there's infinitely many components instead of finitely many, because there's infinitely many values. This is analogous to a dot product. It is an inner product. It satisfies similar properties as dot products. And just as with dot products, you can use them to define a norm. The norm of a function phi is the inner product, a square root of the inner product of the function phi with itself. And then you can use the norm to define a distance. This ultimately defines what it means to be closest. We want to minimize the distance in this abstract space that we can't literally imagine. We just have to trust the calculations. Let's make this concrete. It's still worth, I think, a few more minutes here. Make this concrete by doing some calculations with the computer. Let me clear my kernel just in case there's anything that's going to mess it up. Doing that one just to warm the kernel up. Okay. I can do this stuff in Mathematica. I can define the inner product of, say, phi and psi. I don't have to use a phi and psi, but why not? To be the integral from negative pi to pi. Why negative pi to pi? Because that's a natural interval to use with trig functions of phi of t times psi of t dt. And now I can use this to compute, for example, the inner product of cosine of t with itself, for example, by doing this. And the square root of that would be the norm, the magnitude of the cosine function. It would be square root of pi. If f2 of t is cos 2t, what's the inner product of f1 and f2? 0. f1 and f2 are orthogonal to each other in this inner product space. But you can't literally imagine that, right? You can't literally imagine these functions are somehow perpendicular. They're not in any usual sense. Their graphs don't cross each other perpendicularly. That has nothing to do with it. The reason we say they're orthogonal is because this inner product is 0. That's why. It's not something you can literally imagine. You can only imagine it by analogy. Let's finish things off here by defining these functions. And what else should I use? How about h of t equals 1? And let's do an orthogonal projection of f of t equals t cubed using the formula for orthogonal projections. Is going to be a bit of a pain, but we can copy and paste to save time. Hang with me here. This is important points to make here. What should I call this? How about m of t? I don't know. This, what I'm about to do here, is a bunch of projections. H was the constant function 1. F1 was a cosine of t. F2 was cosine of 2t. G1 was sine of t. And G2 was sine of 2t. What is the formula for this function m of t? It's that. What happens if I plot this along with t cubed? T goes from negative pi to pi. I get that. The orange graph is supposed to be an approximation of t cubed, the best approximation in W. You can see it's not real good. And it gets worse if I make the interval bigger. It gets worse because t cubed in the end is not periodic. But if I added more terms, a cosine 3t and a sine 3t, a cosine 4t and a sine 4t, a cosine 5t and a sine 5t, etc., and did this, all those inner product projections, I'd get a better and better approximation to t cubed for t between negative pi and pi. And t cubed doesn't work super well. You will see in the lecture for t and t squared, it works better. Okay. So we're trying to apply linear algebra, orthogonal projections to these function spaces that are also inner product spaces, with the goal of having Fourier polynomials to approximate the functions, and then ultimately Fourier series, infinite sums of these things to represent them exactly. And that's a good idea for partial differential equations and other applications as well. Okay, I think that will be worthwhile to help you get the lectures better. Okay, if you do take the time to do that, which you should. Have a good day.
Are you